Log on, tune in, find out. Another good idea from Cambridge.
So, so today I will be talking about some properties of the climate system. In particular, I will try to present some results and some perspective related to looking at the climate system as a non-equilibrium thermodynamical system and exploiting this to derive some properties and devise some tools to do somehow to create diagnostics for studying climate models, for studying climate change, and for understanding climate transition. Okay, so let's first I would like to point out some challenges that I see kind of prominent in climate science. So in particular, I think that one of the holy grails that a lot of people are looking at, especially in these recent years, is trying to somehow bring our understanding of climate variability and climate change to a different level beyond the incremental improvements that we have been seeing in the last years. And there's been, these two things of course are closely related, in the literature as well as in public events, the call for the need for a quantum leap in climate modeling. So improving in a qualitative sense our ability to simulate the climate. And in this sense, I think an important direction was given by Barry Saltzman in his book Dynamical Paleoclimatology, where he underlined the need for understanding the global structural properties of the system. How to deal with that? I see mostly two avenues for reaching this that have been historically explored. One has been the one of using low-dimensional deterministic and stochastic dynamical systems, and Saltzman himself was one of the main proponents of this, and these strategies has had a lot of successes, like somehow the understanding of the basic mechanism behind the stability of the thermal circulation and many other properties. Of course, this method has a flaw. The main being that the fluctuations have to be introduced ad hoc, because since it's a low dynamical system, often these dynamical systems are not chaotic. We don't have noise, we have to put noise, and so we go to stochastic system, but the noise we put in is parameterized in some way that is sort of ad hoc. So this, just to say that, of course, all methods have their limitations. I think this is the most serious here, not undermining the importance of this. Another point of view, which is somehow looking at the problem from the other direction, has been the thermodynamic perspective, which was pioneered by Lorentz, which of course enters both domains. And this, when he did analyze the energy cycle of the atmosphere, which is the transformation of available potential energy into kinetic energy, and the understanding of the large-scale properties of the atmospheric circulations then. And interestingly, the atmospheric and oceanic motions on one side result from this mostly. On the other side, they re-equilibrate the energy balance of my system, as especially I think Stone has made clear. And this implies that the problem is a self-consistent one, and this is why it's so difficult. We cannot look at it just from one point of view and hope to get the answer. And recently, I think there was a very interesting work by Don Johnson, who introduced an effective Carnot engine to describe the thermodynamics of the system, and we'll take this line. So the climate, from my point of view, is a non-equilibrium force and dissipative system which generates entropy by reversible processes and keeps a steady state somehow, when parameters are fixed, of course. And a great role in reviving the interest towards a thermodynamic vision of the climate system is due to the literature on the maximum entropy production principle. It's a huge literature, and there are a lot of very good hints. I'm recently actually reviewing a very good interesting paper on this point of view. And there is, as we know, there is controversy about how strong is this principle, how well defined. I definitely think it is, at least in a weak sense, I think it is a very good way to have a first order approximation of the properties of a generic fluidodynamical system. I'm not sure it gives you the right answer, but I would bet it gives you at least a very good indication. So it has to be definitely taken into account. We do not directly, we will touch this in this presentation. And today I'll try to convince you of the relevance of some recent results which connect thermodynamic efficiency and entropy production and cross also this. And I also want to say that there is a different approach, which one could call still thermodynamics, even if it's more statistical mechanics, approach to the climate properties, which is based on a totally different formalism, so some method of non-equilibrium statistical mechanics and ergodic theory. Okay, I'm not talking about this today, but I'm happy to share thoughts about this. Okay, so today first some theoretical work leading us from Lorentz energy cycle, Carnot representation and entropy production, analysis of two cases, onset and decay of snowball Earth, and classical problem of climate sensitivity. Then I will try I will introduce a simplified, very simple way of computing entropy production also from low resolution datasets, which I think can be interesting also in a planetary context, and conclude with an example where I will try to see geoengineering from a different point of view. Okay, so just to see how this thing can be useful. So, and I hope it will be interesting. So starting from scratch, I will go quick here because of the audience, of course. So we take the total energy of the climate system in a domain omega as the integral of the density of the energy, which can be decomposed in the sum of the moist static potential energy, which includes also phase transition, and kinetic energy. And we call P of omega and K of omega these two components, okay? And the energy budget is just the derivative of the energies given by the sum of these two derivatives. Now, it's easier to approach the problem looking at the derivatives of these two quantities. First, kinetic energy budget. Who is depleting kinetic energy? Dissipation. Viscous dissipation, say. Any sort of dissipation of that sort. This is epsilon squared is squared because this is a positive definite functional. And there is a conversion between potential and kinetic energy because that's the only other thing that can happen. This is in the Lorentz formalist. So we have this minus dissipation plus W. I use W because actually this is work, just mechanical work in the very basic thermodynamic sense. Now we look at potential energy budget and we get that it is, of course, this term is opposite of this by energy conservation, and this term is just heating, okay? And the heating is given by two terms. One is this epsilon squared, which was here. Why? Because if we have dissipation of kinetic energy, this has to, it's dissipating, so it goes from macro scale to micro scale. So this, at the end of the turbulent cascade, no matter what, has to become heat. There is no way around. This term is very important, and it's often not considered in climate modeling, and actually this causes energy imbalances, and I will, at the end I will show you a reference where I will work on that, but I will not touch this problem. These are instead the convergence of heat fluxes of any sort. So, of course, the total energy budget is conveniently given by the integral of a convergence, so the flux at the boundary, which we like, of course. So this is a nice, obvious result anyway. So what is the idea by Don Johnson, which I found so attractive? This is the domain omega, and at each instant we do this simple bank-like division between the bank accounts which increase their assets, so this is where heating is positive, and those where net heating is negative. At each instant there will be a boundary which can be as complex as we want, and is not as trivial as this in general, But we can do, it's an operation we can do at each instant. And we will define at each instant the integral over this red region phi dot plus and this phi dot minus without much of imagination. This seems silly, but you will see, will bring us actually to good results. Now, going on, now we go from instantaneous properties to long-term averages because that's what we want here. And this, by stationarity, we have that the average of the derivative of total energy, potential, and kinetic energy have to be 0. Let's see what happens. Applying this, using this identity, we get that the work is equal to the dissipation, which is larger than 0 by the second law of thermodynamics, because it's a positive definite quantity. And then, using this identity, that on the potential energy, we get that the work is given by the sum of the average of this term plus this term. So these two terms do not sum up to 0. This is quite important. And of course, at each instant, the domain change. So this average is defined in a non-trivial way, but we have an operational definition of this. Please. Yeah. Oh, no, sorry, there was a question. So let's see why this, I think, gives us a different view on the Lorentz energy cycle, because phi dot plus plus phi dot minus is the differential heating. This is the conversion, and this is just the dissipation. So here we have rewritten the Lorentz energy cycle using, if you want, just a basic thermodynamic standpoint. And so we start to see that this might be useful. Okay, so this is work by Johnson with the small adjustment I've done. So now let's go to entropy, and at this stage I will neglect mixing, and I will talk about this later. So I will just assume that Q dot is S dot times T by definition, and then the entropy balance of the system is trivially written as this. At each instant, as the derivative of the entropy of the system is rho Q dot plus over T over omega plus the same on the minus domain. Of course, this is positive definite and this is negative definite by the definition of the two domains. I call these two terms sigma dot plus and sigma dot minus. And now, this is the little miracle, I mean, not necessarily miracle, but I think the interesting step, that when I take the long-term average of this, so S dot average has to be 0, this implies that sigma dot plus and sigma dot minus average have to be equal in size and opposite in sign. Okay? So there is this identity that the absolute value of sigma dot minus average this is equal to the value of sigma dot plus, and they are of course larger than 0. This is important if the system is stationary. Its entropy does not grow because there is a balance between the entropy generated by irreversible processes inside the system and the boundary fluxes. So this is crucial here. Let's move along, and now we have energy, we have entropy, and we can basically find a Carnot efficiency, going the other way around with respect to the usual derivation we do in thermodynamics. So basically, we have a constant linking phi dot average to sigma dot average, which we call theta plus, which actually is a temperature inside the domain, because we can use the mean value theorem to obtain this in principle, to define this at least. Obtaining it's very easy, just trick the ratio, and the same for the minus quantity. But what happens is that this guy is in size equal to this guy, but this is smaller than this. So theta plus is larger than theta minus. So this theta plus is the temperature of the hot reservoir and theta minus of the cold reservoir. Result is that work can be written as the net positive influx of heat times this nice expression here, which of course recalls an efficiency. So differences of the temperatures over the larger temperature. So this is the equivalent, the Carnot efficiency of the engine, which is equivalent to how the climate system works. Okay? So this is basically eta times the net input of it gives us the work. We like this. Okay, now we do some steps forward, and we have the following using sort of Landau approach to second principle of thermodynamics. We know that the material entropy production must be larger than a minimal value, which is given by the input of it over the average temperature, which implies that the minimal value, doing some algebraic calculation, the minimal value of entropy production is given by the efficiency we found in the context of the Carnot engine times this quantity, but this quantity describes the internal entropy fluctuations of the system. So the minimal entropy production is the efficiency times a measure of the internal entropy fluctuations. And I like this result. And so there is this link, which is in principle not obvious. But what is the minimum entropy the minimal value of entropy production? What does this mean? It is actually quite simple. The minimal entropy production we can achieve is the one we have when the system when the only contribution to entropy production is given by the dissipation of kinetic energy, because it's impossible for a system like the Earth not to have at least this entropy production in the presence of a dissipation of order epsilon squared, which has value epsilon squared locally. Because if this is dissipated at each instant, this is the entropy which is produced. There is no way of getting rid of it. Okay, so this is the minimal value. And what is the rest? And the rest is the contribution given by the transport of heat down the temperature gradient. So this is the total entropy production, which is given by the sum of this, which is exactly the minimal, plus this other term, which is exactly the conductive-like process. So each time we have transport of heat down a temperature gradient, this is actually the most irreversible process we can think of, and of course it creates entropy. So it is possible to introduce a parameter alpha which quantifies the excess of entropy production and gives to me, from my point of view, a degree of irreversibility of my system, which is the ratio between the excess of entropy production and the minimum. So if it is 0, the system is just producing the minimal entropy production, is as reversible as possible. If this number is large, this means that, well, the system is very, very irreversible. And this is similar to a quantity that in the engineering literature is known as the Bejan number. And so basically, transporting it down the temperature gradient increases the irreversibility, of course, because I am depleting my availability. I'm killing my ability to perform work. So now we can rewrite the total entropy production as the product of the minimum times 1 plus alpha, which is eta sigma plus 1 plus alpha. So if the heat transport down the temperature gradient is strong, eta is going to be small, because we are going to kill temperature gradients. On the other side, if the transport is weak, alpha is going to be small, for the reason I just said. Therefore, I think that one can rethink maximum entropy production, rephrase it as the joint optimization of heat transport and of the production of mechanical work, where this is alpha and this is eta. So I think this is a nice way to rephrase the principle, which I think does definitely make sense to our empirical, at least, understanding of what is going on here. Okay, let's see if this can be useful to define the thermodynamics of the system, to study climate models, and to analyze climate change in a wide sense. Okay, and also, of course, since we are talking about the possibility of the system to perform work, the efficiency of the system, we are talking about the circulation and the feedbacks of the circulation on the temperature field. So climate feedbacks are part of this game, definitely. Okay, we have done extensive tests on a simplified climate model, which is PLASM, which is freely available on the internet, and has been a very good collaboration with Hamburg on this. And then recently we have extended the work also to more complete climate models. Okay, let's start from here. We are setting ourselves in simple settings because we want to see some basic properties of the system. So first, in hysteresis experiment, we take the solar constant, we swing it back and forth by 10%, and we try to observe, to study the transition from the present day climate to a snowball Earth climate. This is a classical experiment, but we'll try to see it differently. So this is the typical graph you see. This is surface temperature. This is our climate. This is very cold climate. Look at the numbers here. Okay, 270, 80 here, 220, 30 here. So this is basically entirely snow covered. This is almost all snow free. This is the present state, which in fact where plasma gives, and it's tuned for giving about 285 or so. We decrease the solar constant. At a certain point, the system goes to this state. So we have here technically the coexistence of two attractors. This attractor dies, and this is where the system is going to go. So mathematically, it's of course, this is not a simple bifurcation, because each of these regimes, of course, is chaotic itself. So we always should be a little careful when using these words, but still, in thinking just in the simple low-dimensional setting. So we jump here, then we go back, and here we go back to the state. So look here, the solar constant is much higher than today, but the temperature is 45 degrees lower, okay? And we have a wide range of B stability. So in this sense, this model gives me a very good snowball Earth, and actually agrees with what you get with much more complex model. So this is the standard picture, okay? Now, so red, warm, blue, cold. Let's go to our parameters and let's see if we learned something. So this is the efficiency eta, and you see that the picture changes dramatically. So in the warm regime, increasing the solar constant leads to a decrease in the efficiency. And who is going to do this? Of course, it's going to be the latent heat, which is going to transport very well when I'm increasing the temperature. In the cold regime, increasing the solar constant actually increases the efficiency. So the two systems are like entirely different worlds. It's not that this is cold and this is warm. It's much more than this. And this state is entirely dry, basically. And so what happens here is that increasing a little bit the solar constant, I can thaw some ice locally, and this drives a very, very strong circulation. And then that's why the efficiency increases. Okay, so this is, so the eta in the S has the opposite sign. And quite interestingly, each time we go across a transition, this is, I think, I don't know how robust, but if robust would be interesting. Each time we go across the transition, where of course we have an exchange of stability in mathematical terms, we have a decrease of the efficiency. Why? Large efficiency, the system is a lot out of equilibrium. Small efficiency, the system is closer to equilibrium. So the mathematical bifurcation has a thermodynamical signature. Decrease of my efficiency. The system becomes more isothermal. Exactly, that's why it's more stable. Okay? Now, let's look at the Lorentz energy cycle, which also is the total dissipation of my system. So the energy input increases with the solar constant in both regimes, but we have seen that the efficiency has opposite behaviors, the result being that the strength of the Lorentz energy cycle decreases in the warm and increases in the cold case. So totally different behaviors also here, okay? Now, entropy production. Okay, this figure looks like the surface temperature, which is first already interesting. So entropy production looks a lot like surface temperature, and it is an indicator. You see there is a good bifurcation. Actually, it's much better than surface temperature, because this number is about 1/4 of this, whereas for temperature the difference was only 20%, if you look at it like in the proper setting. So this is a much better indicator of the two states. And it is a true measure of the of how the system is out, how much the system is out of equilibrium. And of course, the entropy production is monotonic with a star in both regimes. So this is a good, very good quantity to look at. And so I think it's a much better way to define where we are in this hysteresis than temperature. Surface temperature is the average of a quantity which has got strong gradients. In a way, it's not necessarily well defined. It's just an average we do. Here, this is a thermodynamic quantities indicating how the system is out of equilibrium. And it's a good state variable. Now, the question is born here. Why is entropy production growing in the warm state if the Lorentz energy cycle is decreasing, and so the entropy associated to the dissipation must decrease because epsilon square decreases and temperature increases, so epsilon square over T must decrease. Instead, this increases, so what happens is that, of course, my system must have much growing share of entropy production due to heat fluxes, whereas the contribution due to the dissipation of kinetic energy becomes negligible. So that for very warm climates, look, this is diverging, it's 10. So basically, dissipation of kinetic energy is just a small term out of this. Look that in the cold state, this number is stubbornly close to 1. For all, this is a huge range of climate. This means that the two contributions, dissipation of kinetic energy and heat fluxes, are more or less identical, even if they are both changing in this regime. Okay, so I don't know how to interpret this, but I think it's an interesting result. And this might point to a sort of a transition to irreversible greenhouse conditions, but this is something we have not understood yet. Okay, now we can repeat. This has been a huge climate shift, and we want to see climate change, like classical anthropogenic climate change in this perspective. So we change, I'm going to faster here, CO2 concentration from 50 to 1750 ppm, so very wide range. We don't see this stability. This is consistent with what many models see. These are the temperature fields. Surface temperature is linear, more or less, with the logarithm of CO2, as it should be. So we have climate sensitivity in the usual sense of about 2.5, which is more or less good. Whereas the warm and the cold temperature increase by less. They have a lower sensitivity, and the cold temperature increases faster than the warm temperature. So the system becomes more and more isothermal. So we expect that efficiency must decrease by definition because the temperature difference decreases. So this is already a result, and also it's interesting because this means that surface temperature increases more faster than bulk temperature of the atmosphere. So the vertical temperature profile must change. We see it automatically from here. Now this is again a more or less a standard picture. Let's see our sensitivities. So the efficiency will decrease with the CO2 concentration. The energy cycle, the strength of the energy cycle also increases. Entropy production, decreases. Entropy production increases, and irreversibility increases. And look that all these pictures are obviously monotonic with respect to the concentration of CO2, and actually quite linear. So this means that we can write generalized sensitivity of the form d eta in the CO2 concentration, and since all these quantities are monotonic, we can in principle re-express each of them with respect to the other. So as an example, we can rewrite each of these quantities with respect to surface temperature. So this can help us to create simplified models that often use, and when we use sort of box model like approach, or more fundamentally give us an identikit of a climate model if we repeat this for different climate models. And in a sense, these sensitivities are much better defined than the sensitivity of the surface temperature, okay, because these captured some intrinsic non-equilibrium properties of the system. So what are the mechanisms? So let's see what happens when CO2 increases. This is the heating pattern. This is positive, this is negative. Of at 100 ppm, this is at 1000 CO2 ppm. What happens is that the positive region shifts northward. Look, this is 60 south, this is 60 south, and covers here also this area. The fact being that positive heating regions are going to include relatively colder areas, and the opposite for the negative heating regions, which are going to include relatively warmer area. So this means that when we do the averaging I showed you at the beginning of these presentations, the temperature differences will decrease. Okay? And this is how the system becomes less efficient. And this implies that we are going to have a weaker Lorentz energy cycle and weaker surface winds, especially because we must have less dissipation, and a good part of dissipation takes place in the boundary layer and the surface. And the mechanism behind this, as well behind the increase in entropy production, is the change in latent heat transport. This is more or less similar to what we had seen when increasing or decreasing the solar constant in the warm regime in the previous snowball experiment. So now let's make a small step backward. Okay, let's look at entropy balance from, let's say, not first principle, but almost. So S dot of my system is given by the integral over omega of the sum of two terms. Q dot radiative, so the radiative contribution to the heat budget over T, plus this term, which is the turbulent entropy production. So, therefore, entropy production can be defined in two ways. One is minus this guy, which is well defined. You get it in any climate model, the divergence of the radiative fluxes, short and long wave. Instead, this must be constructed. So this depends on the, if you want, on the basic physical balances. This depends on the structure of my fluid. Different fluids will have different expression for this term. Okay, and this is the usual expression where we have a dissipation of kinetic energy and heat fluxes, like the one I showed you before. And there's been a literature, important literature by Paulus Held, Roms, and others, actually pioneered by Goody, which says, look, you don't want to use this because the water vapor, we should include water vapor as an active part. And there is mixing, and there are many other processes, and actually in a different piece of literature, Shinokawa and Ozawa talked about this problem, but from the point of view of the ocean, looking at the solution of salt. So the hydrological cycle has an effect in this, which is not captured here directly. So, how important is this? And this has been actually matter of big controversy also in some recent papers I wrote. And actually, we can make a test. So we see how good is this identity. Because if we use the exact expression of it's trivial to compute. If we plug in different expression of this form, we will get different results. And so there was a paper recently published by Pascal, Gregory, Taillé, and Baum, where they did this, even if not with this purpose, and they got that actually the difference between this calculation and this calculation, so the one I proposed before, it's maybe 2%. So maybe it is not so bad to use this approach. I think this solves a little bit this issue. Where it is correct, this statement, that maybe it is not, it's a second order correction. And actually Goody, who in a paper written in 2000 first presented this problem, obtained again this property, and he said maybe it's by chance. But you know, it's like Sherlock Holmes. If this happens many times, maybe it's not by chance, you know. And you know, we are here in Britain. You don't want to go against Sherlock Holmes. So I agree with them here, at least. Okay. So, and this is a typical number: 50 microwatts, Kelvin -1, and I forgot square meter -1, -2. Okay. So this is I think, a good point. And so let's move, let's move from this expression here, and we use the so-called net exchange framework, which was introduced by Green in '67, which is, let's go from three-dimensional fields, which is what we have to use there, to two-dimensional fields where we use scale temperatures, because this is simpler. This is much simpler to tackle. So using this, we have that looking at the radiative form of entropy production, the entropy production is given by basically processes at the surface, processes in the atmosphere involving short wave and involving long wave processes. So this is what you get. It's like integrating those terms piece by piece and using mean value theorem a few times, okay? These are characteristic temperatures. This is actually what is often done in the literature without maybe mentioning it too much. If we assume that we can define in a more or less in a weak sense at least, in a characteristic atmospheric temperature for short wave, for long wave, and this has to do with the emission temperature of the planet, and this is more or less true. I mean, of course, these numbers will not be exactly the same, but they will be very similar, okay? Where the absorption takes place is in the bulk of the atmosphere. Otherwise, I recall that we will never be able to say bulk of the atmosphere. It means nothing if we don't associate it to some processes taking place. So, assuming that, we get to this simple two-dimensional formula where integration is only on surfaces for the entropy production, where we have two terms, one related to vertical exchanges, and it's related to the net radiative balance at surface, one related to the radiative balance at the top of the atmosphere, which is so related to horizontal heat transport by energy conservation. So this is horizontal large-scale processes, meridional heat transport. This is vertical small-scale processes, which is convection, basically. So we have time and space scale separation in these two elements. So up to now, this is just a scale analysis and division. So we would like to see whether it works, and actually, it does work. We tried it with some climate model simulation, and again, the difference between this number and the number you obtain doing the full calculation is of order of few percent, not more. And this, I think, is interesting because we might think to use this. Look, that we have only two radiative balances, surface and top of the atmosphere. Also the temperatures can be defined all in terms of these fluxes, might be useful to study systems where we don't have such a good three-dimensional approximation. We don't know with such high precision a 3D structure. So now I think that this leads us to consider a 4-box model. The minimal number of boxes we need to study entropy production, I think, is 4, not 2, as usually assumed, not just because 4 is more than 2. So of course it's going to be better, as a reviewer nicely wrote me, and and it was very insightful. But there is a fundamental point. So we have two fluid boxes. They are linked by poleward transport, and this is the usual framework, say, by Ralph Laurenz, which I think, of course, it's a piece of part of the story. And then, but we need to introduce another element. Is the vertical transport between the fluid part, which will be it's the atmosphere, is the surface ocean. This is not it's what is able to transport. That is the point. So then it's a sort of a 2 times 2 box. Okay, where we have a horizontal coupling occurring only at this level because surfaces cannot couple each other, cold and warm surfaces, and vertical coupling of this sort. So I think this is a better frame. And then we tried this. This is ADCN3, and this is S vertical, and where we see that most of the contribution comes, guess what, from the tropics. And look that we have the warm pool, the nice structure, and look, I think it's interesting that red dots come in tropical forests, which acts as if they were oceans, because they're very humid, of course. So I think there is an interesting link here. The horizontal part, instead, that has a negative component here, because entropy is the flux of entropy is in this way. The numbers here, you cannot read it, are 5, the scale is 5 times bigger, but here it is always positive, because we are looking at the reequilibration in the column. Here we have, of course, negative terms, which is nothing strange, because this makes sense only when integrated globally. Who wins when we integrate both? And the result is that this contribution wins by 1 order of magnitude. So, vertical processes contribute to entropy production about 10 times with respect to large-scale heat transport. These are all the IPCC models in last fourth assessment report. And this is a very consistent result. And nicely, IPCC models actually agree quite well on these numbers, which is surprising to me, because I've looked a lot of climate diagnostic, and this is the one where they agree the best, which is good, I think. And interestingly, we'll not publish this yet, nor submitted, in a warmer climate, the horizontal contribution goes down and the vertical contribution goes up, which again gives us a decoupling between these two processes, which is quite consistent. We have done some calculations also on Venus, Mars, and Titan, and we'll see numbers in a sec. Other elements is that if you now look at the simplified formula for material entropy production and apply the same net exchange framework, we obtain, we can work it out, obtain some expressions where we have fluxes of sensible and latent heat exchanges between surface, basically, and the atmosphere, and taking some approximation which basically are related to the fact that sensible heat fluxes are confined in a small domain, and latent heat fluxes instead go from the surface to the mid-troposphere. Taking some reasonable approximation on the temperature, one obtains this result that the term related to entropy production due to horizontal motion times a characteristic temperature of the planet gives us a lower bound to the intensity of the Lorentz energy cycle. This again looks pretty much like basic thermodynamics. And working this expression, you find that this minimal value of entropy production is given by the net radiation entering at the tropics, or the net radiation going out in the polar regions, times a baroclinic efficiency. And this term has been introduced in a recent paper by Thorburn and others published in Nature, where they found it using scaling arguments on atmospheric transport. And this is a thermodynamic way of deriving it. It's exactly the same expression. Okay, and the two characteristic temperatures are the average temperature where the net radiative budget is positive, and the characteristic temperature where the net radiative budget at the top of the atmosphere is negative. So naturally, equatorial regions versus mid-high latitudes. This is a, let's say, macro scale vision of the problem. And then we can play this with planets, because we have these numbers. These are just celestial objects which are near to our planet. We can get all these numbers. And note that if we rescale the input of energy, all these numbers with respect to the input of energy, so we assume, of course, Titan has a much lower energy input than Earth, than our planet. If we make, the energy, we rescale the problem in such a way that the input is the same for all, so it's just like a scaling. Actually, finally, we get that some of these numbers, the efficiency, the flux, the entropy production, are within 1 order of magnitude, even if these planets are entirely different. This is something we still are thinking about. I don't know how much sense it makes, but I think it's a strong, quite interesting result, because it is related to the thickness of the atmosphere of this planet. So Venus, Titan, and Earth are thick. Mars has instead a thin atmosphere. So, but okay. Last thing I'm going to briefly talk about today is geoengineering, which is of course a word we have been hearing a lot, might be too much. in the last years, it's interesting, very interesting issue. So geoengineering is large-scale modification of the climate done on purpose, basically, to compensate adverse effects of climate change. Okay, there are a lot of ethical, scientific, epistemological reasons, which I'm not going to discuss today. And to me, what I'm interested in is that this is a non-trivial example of constrained climate change. I'll see why it's climate change, not climate not change as its intention. It's a family of this problem. So what is geoengineering? Geoengineering is about choices, and it's about isolines. So I am increasing CO2, and I want to give an input of aerosols to such that average surface temperature is constant, or average atmospheric temperature is constant, or average sea surface temperature is constant, or maybe surface temperature in the lands in the mid-latitudes in the northern hemisphere is constant, okay? So it's a political choice. It's not, I'm not changing climate. Because along each of these isolines, the other climate parameters will change. We are fixing one observables, but we don't care about the others, okay? So this is something that should be emphasized. It is a fact. It is a well-defined mathematical issue here. There is not that there is no. It's a well-posed mathematically, but then this means something. Okay. So the idea I would like to propose is let's choose some of these isolines, which we can find by construction. That's the way the experiments are done to study geoengineering, and then along each of these isolines, we can study how the global thermodynamics of the system changes, and then relate this to changes in properties which are of great interest, like storm tracks, El Niño Southern Oscillation, monsoon, which are small, or I mean small to say, large scale, that they are related, they are like large scale realization, it's large scale phenomenology of the global thermodynamic properties we have seen before. Of course, this is related to the baroclinicity and the efficiency. This will be related to vertical processes. This will be related to atmosphere-ocean coupling. Okay? So, concluding, I hope today I proposed something which links energy cycle to maximum entropy production in a way that can be useful. We have shown that this is useful to study large-scale climate transition as well as climate like CO2 sensitivity, so classical climate experiments, and we can derive a 2D simplified formula which allows us to decouple vertical and horizontal processes, thus allowing to study large GCMs as well as observative data. Many challenges: studying the GCM's performance in a new way, studying climate tipping points, and maybe the possibility of reviewing something related to biosphere and climate interactions, which, by the way, has been a very crucial stimulation for the whole thermodynamic understanding of the climate system. I mean, there is a huge literature that I'm not going, I mean, there is an important group which meets more or less regularly, usually in Jena, organized by Axel, Clydon, Roderick, and others, where this is an important point, and I think it's very interesting. And maybe we can start to think more precisely about the thermodynamics of celestial bodies. There is also some interesting basic macroscopic thermodynamics to be worked on, that using some more modern views of Carnot engine, which can be implemented related to endo-reversible thermodynamics. And also I underline that there are other ways to approach some of these problems, which are related to statistical mechanics, which take a different path but can help us to see this problem in a different way, to study climate change sensitivity and climate prediction, actually. So I'm working on this now in the context of this European Research Council project called Namaste, and of course I'm very happy to have inputs or proposal of collaborations. These are some references. I thank you very much for your attention. Roderick.
That's a very nice talk. You showed a plot of the horizontal and vertical entropy productions
Yeah.
of the different IPCC models,
Yes.
which showed there were convergence in terms of the horizontal, but not in the vertical.
Actually, if you depends on the scale. Look, this number is about 5 milliwatts, and this is about 50. So here, the discrepancy. This model is a different story, but let's look at the bulk of this model. It's about 10%, which is good. This number is 5, so it's more like 40% different, like the range. So this seems actually in a way less well constrained than this, in relative terms. There is an interesting fact, is that if you look at this disagreement is larger than the disagreement in the meridional heat transports of the same models, where you would suppose the opposite, because you think, okay, this comes from basically the competition between flux and temperature difference. So you assume, okay, if a model has a larger meridional heat flux, it should have a smaller meridional temperature difference. So the two terms should compensate. So my a priori expectation is that the agreement in this entropy production should be better than the agreement in the meridional heat transport. Instead, this is not necessarily the case. So there is some physics which needs to be understood there. This is okay. Then I will show you the paper where we look at the energetics of the system. So this is a step after. And you see, this is the numbers that usually we get in the simple two-box model, in fact, 4, 5, 6, depending on how you tune them. Okay, I don't know, other comments or? Okay, okay, if not, I think maybe we can stop here. I'm going to be around and happy to discuss this and other stuff later. Okay, thank you very much.